Welcome back. Today we're going to be doing 5 multiple choice and 3 long answer questions related to the power rule in calculus. So let's dive in. So, reminder really quick, what is the power rule? The power rule states that if our original function is x to the power of a, then the derivative is equal to a times x to the power of a minus 1. So basically we take the power, we put it in front so it becomes the coefficient, and then we subtract 1. So for this one here, x to the power 5, I'm going to take the 5, put it in front, and then I'm going to lower the 5 in the exponent by 1. So the 5 becomes a 4. And so the answer is A. It'd be this one. All right, let's try another example. This one asks about the derivative of 1 over x cubed. Now recall that 1 over x cubed is the same thing as x to the power of negative 3. And then when we take the derivative, I'm going to take the negative 3, put it out in front, and then I'm going to lower the exponent by 1. So what's 1 lower than negative 3? That'd be negative 4. And so the answer is this first one here again. Okay, here's another example. If f of x is equal to, h of x is equal to the quarter root of x cubed, then what is the derivative? Okay, so here's the thing. We know that the quarter root of x cubed is the same thing as x to the power of 3 over 4, right? Recall that putting a root to something is the same thing as having that number in the denominator of the exponent. So I move the quarter root into the exponent by putting it in the denominator. And then we can use the power rule to find the derivative. So I'm going to put the 3/4 out in front, and then x gets repeated. And then what is 3/4 minus 1? So 1 less than 3/4, that'd be negative 1/4, right? If we did 3/4 minus 1. And so the answer is A. We seem to be getting a lot of A's. The next one asks, which function has derivative 2x? All right, well, let's see. The first one here, if we take the derivative of the first one, x squared, we do get 2x. If we take the derivative of 2x squared, we would actually get 2 times 2x, which is 4x, so that one wouldn't be right. The third one says f of x is equal to x squared plus c, where c is a constant. So the thing is, the derivative of x squared would be 2x, and then the derivative of the constant would just be nothing, right? So this would just be 2x plus 0, which is equal to 2x. Or the last answer is all of the above. Now here's the thing. We know that actually it can't be all of the above because it's definitely not B, but actually both A and C do have this derivative. So I'm going to say it's answer A and also answer C as well, because it's x squared plus any constant, including potentially 0, could be that constant, right, as it is in x squared. All right, the next one asks, the power rule applies to only positive integer exponents, only polynomial functions, any real number exponent, and only rational exponents. So the answer is C, any real number exponent would work, even if we have x to the power of 2.5, for example, or x to the power of pi, or x to the power of really any real number, the power rule still applies. Now, oftentimes in practice, we'll more likely see polynomials, positive integers, rational exponents, all that, but technically it does work for all real numbers. It does not only apply in these certain cases, even if these are the cases that we use it most often. Okay, now let's get into these questions here. We start with x to the power of 2/3. We want to find the derivative. So the derivative for that is going to be where we put 2/3 out in front, so 2/3. And then we have x to the power of 2/3 minus 1. Now what is 2/3 minus 1? That would be negative 1/3. So the answer would be 2/3 times x to the power of negative 1/3. Now we could leave it like this, or if in your school the teacher does not like negative exponents, you could also put this in rational form as well, or radical form rather. And you could say, well, this is also the same as 2/3 cube root of x as well. Because recall that the negative in our exponent means take the reciprocal, so put x to the bottom because of the negative sign in the exponent. And then because of the 1/3, well, what's x to the power 1/3? Recall that that's the same as the cube root of x, right? Power of having a denominator as our exponent means that's the root we take it to. Okay, let's try the next one. 2 over x to the power of 5. So first thing I'm going to do here for stuff like this is I'm going to put this in the numerator. So recall that x to the power 5 in the denominator is the same as x to the power of negative 5 in the numerator. So this is the same as 2x to the power of negative 5. So the derivative, the first thing we would do is we would put negative 5 out in front as the coefficient. So we've got to multiply it with the current coefficient of negative 2. And 2 times negative 5 is negative 10. So we'll get negative 10. And then we'll have x to the power of negative 5 minus 1, because we lower the exponent by 1. And then that's going to be negative 10 x to the power of negative 6. Now, if you don't like negative exponents in your answer, that's fair. If that's the case, we can just move it onto the denominator and get rid of the negative sign. So we would have 10 over x to the power of 6, like that would be a way to get rid of the negative. All right, let's try part C. 3 times the square root of x minus 4 over x squared. So both of these at first look a little bit confusing as to how we would use the power rule. So first thing I'm going to do is put both of these in exponent form in the numerator. So recall that the square root of x is the same as x to the power of 1/2. So let's write that down. That this is the same as 3 times x to the power of 1/2. And then 4 over x squared is the same as 4 to the power, or 4 times x to the power of negative 2. Okay, now this looks like something that we can actually use the power rule for 2 times, one for each term. So we'll take the power rule here and the power rule here as well. So the derivative for this first part of 3 times x to the power of 1/2, if I multiply 3 by 1/2, I get 3 over 2. And then what is 1/2, which is our current exponent, minus 1? That would be negative 1/2. And then for the second part, we have negative 4x squared, or sorry, x to the power negative 2. So I'm going to multiply the negative 2 in the exponent by the negative 4, which is our current coefficient, to get positive 8. And then we have x to the power of negative 2 minus another 1, which gives us negative 3. Then, in order to get rid of having negative exponents, if that is something that your teacher cares about, which some do, some don't, it just depends, we're going to remove those. So we're going to end up with, over here, 3 over 2 root x, or 2 times x to the power 1/2 in the denominator is fine as well, because recall that x to the power 1/2 is the same as square root of x, and that the negative means move it down to the bottom, right? Negative means if it's in the numerator, put it in the denominator, and if it's in the denominator, put it in the numerator. Same with over here, we have x to the power negative 3. The negative means move this to the denominator to get rid of the negative sign. So x over, or 8 over x cubed, would be our final result for that one. All right, the next one says a particle's position is given by s of t is equal to t cubed minus 4t squared plus 6, where t is the time in seconds. Find the velocity function, the acceleration function, and the velocity at 2 seconds. Okay, so recall that the velocity is equal to the rate of change of the position, right? At what rate is the position changing? And so therefore, we would take the derivative of the position function to get the velocity function. So what is the derivative of this function? Well, derivative of t cubed would be 3t squared based on the power rule. Then minus 4t squared, we would put the 2 out in front, so we get negative 8t. And then recall that the derivative of a constant like 6 just becomes 0. So that's the final answer. We don't have to do anything about the 6. In fact, it wouldn't matter which constant this was for our velocity. If the constant was something else, we would still get the same velocity here. Okay, what about the acceleration? Well, recall the acceleration is equal to the rate of change of the velocity, which is the derivative of the velocity. So now we're just taking the derivative of this right here. All right, so what's the derivative of 3t squared? We'll multiply that 3 and that 2 to get 6. And then 2 minus 1 gives us 1. So this would just be 6 times t to the power 1, or 6 times t. And then negative 8t, recall that that's just going to become negative 8 because the 1 just gets multiplied by the negative 8. And then 1 minus 1 gives us 0. And what's t to the 0? Well, just 1. So it's just going to be 8 there. And there we go. The last question asks us to find the velocity at t equals to 2 seconds. So what I'm going to do for this is just sub in 2 for this equation, the velocity equation. So that's going to be 3 times 2 squared minus 8 times 2, which is 3 times 4 minus 16, which is 12 minus 16, which is negative 4. So therefore the velocity is negative 4. Oh, I'm just realizing can't see all that. There we go. Yeah, so it would be negative 4 just by plugging in 2 to the velocity equation that we found. All right, let's do one last one. It says to explain why the power rule cannot be directly applied to find the derivative of 2 to the power x, and asks what additional rule would be needed. Okay, so the reason is because the power rule applies when x, or a variable, is the base and the exponent is a real number, right? So it works when we have x to the power of a, where a is a real number. In this case, we don't have that though. We have a fixed base, which is 2, and then we have a variable as our power. And so that's why this isn't going to work. We're not going to be able to find the derivative of this using the power rule. In addition, we would need the exponent rule, which we won't get into today, but we would need the rule for what to do if in the event that the exponent is a variable, or what if the exponent has some variable components in it, right? What if this is an entire polynomial here as our power? We will get to what to do for that, but the power rule would not actually help us for that situation. As always, if you have any questions, feel free to leave those in the comment section, and we'll see you for the next one.